Let's talk about how to read a pedigree. These are fantastic for looking at an entire family history to see if we see the expression of a particular trait. Now, to distinguish between males and females, we use different shapes. Specifically, we're going to use a square to represent a male and a circle to represent a female. If it is not shaded in, then these individuals are not affected. If they are shaded in, they are considered affected. So notice how a dark filled in square represents an affected male. Now if we go down to our fifth symbol, the person whose sex is not known. This usually is going to refer to an individual that has not been born yet, or was an individual that was a miscarriage and sex had not been determined yet or had not developed far enough yet. This could also represent an individual that we knew was a sibling of someone else in the tree, but we did not know if they were male or female. Next, we can discuss marriage, or rather a mating. As most individuals know, you can have a baby without being married. So we see a line going between two individuals represent a marriage. Under that we have a consanguineous marriage. Con meaning with, sang referring to blood. So these are blood relatives that have joined in a union. You typically will not find these in most pedigrees, but if you do see the double lines, now you know. If you see a vertical line, as we see in the upper right image, these are going to represent an offspring. And here we have a son denoted by a square. On the next image, we see an entire family, a father, a mother, and 4 siblings. We have 2 brothers and 2 sisters. On the far right, we notice that there's a strange triangle shape when it comes to this particular set of siblings. These are fraternal twins. If they were identical, they would have a line coming off of the point of the triangle, and also we would note that they would have to be the same sex. Now we're going to look at 4 examples of different pedigrees, and each of these examples will be an example of autosomal dominance, autosomal recessiveness, X-linked dominance, or X-linked recessiveness. And when we're looking at a pedigree, the first thing that we're going to look for is there a discrepancy in how many males are affected versus how many females are affected? This will help us to eliminate possibilities. So for example, if we see a discrepancy in, say, having more males than females, we can actually assume that it's going to be X-linked, and specifically X-linked recessive, and we'll actually go through a couple of Punnett squares when we get to that particular slide. The first I want to take a look at, now we have a few different generations going on, 1 and 2 being our initial generation, where the ultimate grandfather had the particular disorder. Now when we're trying to determine if this is autosomal or X-linked, typically we start looking from generation 2 downwards, and we notice that we have 4 individuals that are male and 2 that are female. At this point, we would say this could be a case of sex-linked traits because we do see a discrepancy when it comes to males versus females. But this is actually a relatively small sample. We were looking at pedigrees if we want a definitive answer. In a lot of cases, we need to make sure that we have enough individuals to look at. The area that I want to focus on is going to be right over here. And I'm going to grab a felt tip pen. And I want to take a look at this portion of the family because I have 2 affected parents and I end up having non-affected children. Let's say that this was an X-linked recessive gene. This would mean that dad would have to be a recessive gene on the X, and he has a Y chromosome. Now, with the Y chromosome, this counts as a null or a 0 because the Y gene is not going to carry this particular trait. And mom, if it is X-linked recessive, means that both copies of her X chromosome must have the recessive allele. If this is the case, we can draw a Punnett square, like so. And on the top, I'm going to put dads. So X little r, Y null. And over here, we've got our female XX. And she is homozygous recessive for R. And I just chose R just because it was an easy letter for me to think of at the time. So now notice that in our square, this half of our children are going to be females, and this half are going to be males. And in all cases, the individual would have the recessive trait, which means that all three of these individuals would have to express that particular trait. And as we see, we have two individuals that don't. So it can't possibly be X-linked recessive. The next thing we're going to look at is the fact that I have two affected parents. And if this was an autosomal recessive disorder, then we would notice that all the kids would have to have the particular set of genes. They would have to be little r, little r. And once again, I have two unaffected people. So this means that it is going to have to be a dominant disorder. Is it going to be X-linked dominant, or is it going to be autosomal dominant? If we look over at 3 and 4 here, we notice that 4 is an affected male. So that means that that particular male would be X big R Y null. Since we have two daughters, that means that each of them would inherit an X with that dominant trait. So both the females would have to be expressing of the trait. So we've ruled out X-linked dominant and X-linked recessive, autosomal recessive, so the only possibility is autosomal dominant. So that means that we would have to have a big R, little r for dad, and a big R, little r for mom. And if we draw our square right over here, it's not the prettiest square, but it gets the job done. Big R, little r, big R, little r. So in 3 of these cases, I'm going to have a dominant allele. So that means that most of the time we are going to have expression of the trait, but in 25% of cases, we're not going to have any expression. All of our kids here are unaffected, and we have 2 out of 3 unaffected here. So when we say 25% of the kids would be expected to have the recessive trait, that doesn't necessarily mean that that's exactly what's going to happen. It's all probability and chance. So in this particular case, we know that this must be autosomal dominant. Let's look at another example. So the first thing that we notice is that we have 3 affected males and no affected females. In this particular case, we may just automatically assume that these individuals are all going to be X-linked recessive trait holders, and that would be a valid guess. It could be something else though. So let's say that this could be autosomal recessive. That would mean that dad here is little a, and it doesn't really matter what mom is. We'll say a question mark. And we know that down here, we've got little a, which means that we had to get a little a from mom, a little a from dad, and we've got the dominant alleles because they are affected. So this shows us that it could be possible that this is an autosomal recessive trait. And the only way that we could really figure out if it was X-linked dominant, or rather X-linked recessive or autosomal recessive, is to have a bigger sample size, or if we actually did a genetic screening on these individuals. Now, this third one is a fantastic example of having a relatively large sample size. If we look from generation 2 down to generation 4, if we count our males, 1, 2, 3, 4, 5, and 6 males, and I've got 1, 2, 3, 4 females. So there is a small discrepancy, but not enough for us to think, oh, this must be an X-linked trait. So that means it's most likely autosomal, and our eyes are really drawn to this particular part of the table because everyone in this corner has the particular trait that's all being expressed. Both parents have this particular sequence. They have this particular trait, and all 4 of their offspring have it as well. This is indicative of autosomal recessive. Now, with autosomal dominance, yes, this could happen. In most cases, it would happen. But we have to look somewhere else. Specifically, I want to look at this middle section because I have two affected children with 2 unaffected parents. If this was autosomal dominant, then we would expect that at least one parent would have to be affected. But in this particular case, neither parent are affected. So this rules out any form of dominance when it comes to determining the expression pattern. So we know that it must be recessive, and it's most likely autosomal recessive because it is affecting these 2 individuals at the same rate. Both males and females are going to be affected. We also can suggest that this isn't recessive because our father here would have to be a recessive carrier and thus would have to have it. For 7 to have been able to get this, if it was autosomal or if it was X-linked recessive, mom would have to have this combination. So she would have to be a carrier, and dad would also have to be a carrier. But if dad's a carrier, then he would have the disorder. So that's not going to happen. And we also notice that this female is unaffected, so it can't be that. And once again, it can't be X-linked dominant because one of these parents would have to have that particular trait. And finally, I have our 4th example. This time I have 1, 2, 3 males, and I have 1, 2, 3, 4, 5, 6, 7, 8 females. So I have almost 3 times as many females as I have males that have this particular trait. In this case, we would take a guess and say that it's an X-linked dominant disorder. And one of the sure ways of seeing this is in our initial cross. Dad only has 1 X to give. So he is going to have a genotype of this, assuming that is X-linked dominant. And all 3 of our offspring are women, and they all got this particular X chromosome from dad. Mom could be XR X little r if it was recessive, and it is possible that if this was recessive trait, that all the women could technically have it, but that's rather unlikely. If we look down here, we notice that mom here did not give rise to an affected son. We have an affected son and an affected daughter, but this son is unaffected, so it's very unlikely that is an X-linked recessive trait. So we've now gone through 4 examples. 3 of them are very clearly going to be autosomal dominant, X-linked recessive, X-linked dominant, but we did have the one earlier where it could go either way with X-linked recessive or autosomal recessive. Pedigrees can get us to that particular point, but we have to actually look at some genetic screenings to actually fully determine if something is X-linked or if it's autosomal. I hope this helps to clear out some misconceptions about pedigrees and hope that it helps you when you're studying for your test.